All right, I'm going to go ahead and do part B of homework 2 for separations, starting out in Python here. So what we're going to do today is we are going to find the activity coefficients for multi-component mixtures in two different ways. The first, we're going to be using the excess Gibbs energy expression of the NRTL model, which says that just on the Wikipedia page here for the NRTL model, the Gibbs IJ is going to equal E to the activity coefficient times tau, and then tau is calculated by a bunch of empirical constants that we're going to pull from our CHE tools library. So in Colab, this equation is going to take the following form. We are going to have tau ij. Let me pull this out. I have tau ij is going to equal, looking at the Wikipedia page here, our aij plus b over bij over t plus cij times the natural log of our temperature plus dij, I believe, times t. So that's the form that this equation is going to take. But to get us started here, I first have to put in our components that we're finding this activity coefficient for, our isopropanol, our water, and our toluene. So we're going to say that P is going to equal props, say isopropanol, water, isopropanol, water, toluene for our three component mixture. Then we can go ahead and create our function. I'm going to say that we're going to define GEX underscore NRTL as a function of X temperature. And then we need to find our tau as described up here. So we're going to say tau is going to equal our A, which we're going to pull from our CHE tool libraries. We're going to say P dot NRTL A. And then as up in that equation, we're going to add our B's. We're going to say P dot NRTL B over T. And then we're going to add P dot NRTL C times Jax NumPy dot log of T. Finally, we're going to do P dot NRTL D times T. And that gives us our tau function, but we're looking for our activity coefficient. So to find that, we are going to say that our G, our Gibbs energy, is going to be equal to jmp.exp minus tau times our NRTL alpha value, or p.nrtl alpha value. And then we are going to get our tau g, our tau multiplied by our Gibbs free energy. So we're going to say tau g is going to equal tau times g. And then we're going to do our tau gx, which is where our Jax NumPy einsum comes in to create this matrix that we're going to multiply. So we're going to say tau gx equals Jax NumPy dot einsum. And we're going to go from ji to j goes to I. put in our tau g x. Then we're going to call our gx jmp dot einsum is ki k goes to I of rg or x. And then we're going to return x times tau gx, not capital tau gx over gx. All right, shift enter. So now that we've got this function, we're good to do our Jack's automatic differentiation to find our activity coefficient. So to do that, we are going to Gex gradient, our GEX gradient is going to equal Jack's dot grad, which is going to give us that automatic differentiation we're talking about of our GEX NRTL and starting at 0. Hold on. I realized yet again I forgot my sum that is crucial to this. Sum. And I also should not have put that. Fantastic. All right, now we've automatically differentiated this function. So let's go ahead and find this activity coefficient. All right, now we can actually put in our provided problem metrics for this so that we can actually solve for our activity coefficient. So we're gonna create an array of our x's. We're gonna say x is going to equal np.array. And we're going to have 0.3, 0.3, and 0.4 for our liquid compositions for each of those components. And then we're going to set our temperature equal to 300, as it says up above. And now we can finally get our activity coefficients using our GEX NRTL above. So we're going to say jmp.expand, take e to the power of our differentiated function, grad, at this x and t we provided up above. Fantastic. So those are our 3 activity coefficients for our first method using the excess Gibbs energy expression to find where our excess Gibbs energy can be minimized to get those activity coefficients. So that's our first method. So let's go ahead and move on to our second method. All right, now moving on to our second method, the direct calculation from the NRTL activity coefficient model. We are going to copy over a lot of the stuff that we had previously here, but we're going to define NRTL as again, a function of x and t. And we're still going to need our tau. So all of this stuff we can bring right over down here. Except this time, since these are different variables, we are going to put the x out front here. So x tau g, xg. Now we need to do something called broadcasting to get these. These currently are 2 matrices of different sizes. So this top one is 1-dimensional and this bottom one is 2-dimensional. So we have to use some broadcasting to get both of these to be 2-dimensional arrays so we can work with them. So to do that, we are going to create this variable x tau g divided by xg, and that is literally what we're going to do. We're going to take our x tau g divided by xg. And then moving on from there, we can return JMP xp of our x tau g divided by xg plus our JMP einsum of our j ij goes to I x g times tau this all times or tau minus r x tau g divided by x g none all divided by x g. And then finally, to spit out our values for our activity coefficients, we're just going to say nRTL at x and t. Shift enter. And look at that. We get the exact same coefficients through this method of using the direct calculation versus the excess Gibbs energy calculation up here with our gradient. So that is how we found our NRTL activity coefficients through those two methods. I believe that is the end of my separations homework 2 part B. So I'll see you in the next one.